Well, good morning. Thank you all for coming. And so, it's a great honor and privilege, as I mentioned before, to come and teach and present, this particular class on recent topics in multiphase flows at IIT Kharagpur. I'm going to talk a little bit about myself, as a part of the morning lecture. But I heard that there are a few students from IIT ISM Dhanbad. So, I actually was born and brought up in Dhanbad. I went to Dinobli school and before coming to IIT Kharagpur. So, that's a double reward for me essentially, having to present at IIT Kharagpur and also meet with students from IIT ISM. I came this close to actually becoming a student in ISM, and but I joined IIT Kharagpur instead. And as life would have it, I came and did my bachelor's in mechanical engineering over here. But at Texas A&M now, my primary home is in mechanical. I am a professor there, but I have a joint appointment in petroleum engineering. And at the time, I was considering joining the petroleum engineering department at ISM. So with that started, so so let me start by talking a little bit about this particular class. So I guess the Indian custom is to start with Guru Vandana. So I would like to dedicate some tributes to my professors here at IIT Kharagpur, and also my the multiphase flows work that I am going to be talking about for the next 5 days. Of course, I learned that with my PhD advisor Professor Vijay Dheer at UCLA. Also did some work with Professor Shuman Sinha, who is also alumni of IIT Kharagpur. He was my master's advisor, but it all started over here, in terms of learning fluid mechanics from Professor Das, and then doing my undergraduate first year mechanics with late Professor Mandakani Mujumdar. So come to think about it, 30 years ago I was here in IIT Kharagpur doing my what do you call it, the admission process, essentially the counseling essentially. It was exactly 30 years ago that I came here for my counseling, trying to decide which department I want to join, and of course mechanical was my first choice, and I was lucky I got it. And so I learnt my thermodynamics with Professor P.K. Nag, my fluid mechanics with Professor Mohanty, HVAC with Dr. Arora, and so on and so forth. So it's kind of in Bengali they call it hate khuri. So my engineering education started here, and so I would like to dedicate this particular course to all my professors here in IIT Kharagpur, currently who have passed away essentially. And it's very nostalgic for me to come and do the presentation here. And so I was looking around on the website for all the professors I knew who have passed away, but unfortunately only these are the only 2 pictures I could find after doing a online search. Now after Guru Vandana, of course you want to do a Shishya Vandana also, because all the breakthroughs and knowledge that we generated in our research group was actually the hard work of all my students in my lab. And particularly I am indebted to the 13 PhDs and 18 master's students who have graduated since 2005 after I joined Texas A&M. And over summer usually I have research undergraduate students coming and doing research over summer, and then of course there are a few students who do research all through the year. So over the 13 years or so, we have had about 40 undergraduate students doing research in my research group, and out of that we generated about 3 honors theses, and about 12 women and minorities also participated. But the whole story would not be complete without acknowledging 2 other students in my research group. So this is how my research group looked like when I started in 2005, and 2007 is when sort of my group ramped up. And so we have this group picture thing taken every 6 years, and you can see how the group has changed over the years. But I also usually joke that we academicians are on the dark side. All of you watch Star Wars, right? Have you all watched Star Wars? And so the bad guys, what kind of army do the bad guys have? The ones on the dark side. The ones with that plastic mask, what are they called? Anybody know what the name of that army is? What's that? Stormtroopers? Well, yeah, they go under the generic name clones. So we academicians, I joke, are on the dark side. We like to create clones of ourselves, and so I'm proud to say I have created 2 clones of myself. Navdeep Singh, who's at University of Houston, and then Dong Shin, who's from Korea. He is at University of Texas at Arlington, and so what I'm going to be discussing today, all the new knowledge, all the recent advances that we have made in our research group are because of all these hardworking students, and I have been very lucky. I have gotten some really good students. I don't know how they found me, but they came to my group, they made all the breakthroughs, and some of those we are going to be discussing in the next 5 days. So the learning objectives, as I see it, I'm going to start with this concept called convergence. So the National Academy of Engineering in United States, every 4 or 5 years or so, they come up with a policy document in terms of where engineering and science and math education should go and how it should evolve. And so this new concept they have come up with is, it's not actually a very new, but it has recently gotten a lot of recognition. It's the concept of convergence. And I figured, we are going to be talking about multi-phase flows, which is a very specialized topic. And so instead of being in our silos, it's also good to have a big picture of the world around us and how we fit in and how we contribute to society. So I would like to start with this concept of convergence, discuss it a little bit, so that you understand in terms of it's not just the science and the math of what we are doing, but there is a bigger picture out there where we can contribute to society. And then I'm going to start off with the instability theories, and then look into the extension of these theories into the recent topics in terms of nanobubbles and nanodroplets. And then I'm going to talk about pool boiling and condensation, just to go over the basics. But the real aim of this particular class is to get into the advanced topics. 13 years or so, there has been a lot of activity, lot of funding, lot of papers, and in 2005 we were the first research group to apply carbon nanotube coatings to heaters to improve boiling. And even to this day, the early students who worked on it, particularly Vijay Satyamurthy, he was the first one to generate the complete boiling curve, both in nucleate boiling as well as in film boiling, using carbon nanotube coatings. And to this day in the literature you will find a lot of papers on carbon nanotube coatings for boiling, but they are all in nucleate boiling, and there hasn't been any other studies on film boiling. Okay, and there are some extensions to applications in nuclear energy, particularly with respect to nuclear safety, that I'm going to highlight on Friday, when I get into those topics. But the basic goal of this particular class is on you this new concept that we have come up with. We call it the nanofin effect. Okay, and what we found was we were doing experiments with nano coatings as well as with nanoparticle additives, or what are known as nanofluids, and we started getting very counterintuitive data. For example, we found that a nanotube that has a lower thermal conductivity was giving us higher boiling heat transfer, and of course you cannot violate the laws of thermodynamics. So in order for us to figure it out, we had to resort to dynamic simulations, molecular simulations, to resolve that conundrum. Okay, so I'm going to talk about nano coatings, I'm going to talk about nanofluids, and then we also developed these nano sensors or nano thermocouples that we use to measure temperature fluctuations during boiling. And to our amazement, we made another discovery. We found that boiling actually is fractal. Okay, so Friday, if I have some time, I won't get too much time to discuss about chaos theory. It's based on information theory, so I won't have too much time to get into the basics of information theory, but I'm going to present some of the relevant results that we got in terms of fractals and chaos in boiling, but I won't get too much time to discuss that. The focus of this particular class will be to get into the nanofin effect, why certain counterintuitive behaviors come at the micro and nano scale. And then of course, we are also going to talk about micro and nano channels or micro nano fluidics. And one of the things we have found that there is a big application in oil and gas, particularly with respect to oil exploration and production of what is known as shale oil or shale gas. So United States, for example, just like India until about 10 years ago was a net importer of oil, and after this hydraulic fracturing technology came about and got implemented, now US has actually become an exporter of oil. And I think there is a big potential in India also to go that same route. And so some of the conundrums we are facing with respect to producing oil in from shale rocks using hydraulic fracturing, it has to deal with flow of hydrocarbons, multi-phase flows in nanopores in shale rocks. And so I am going to talk a little bit about it today, but the bulk of that discussion will be when we get into the advanced topics, more on Thursday and Friday. Okay. So that's basically the learning objectives for you for this particular Gyan course. But I'm open to suggestions. If there are other aspects that you want to or for me to highlight, feel free to let me know during the break. And by all means, if you have any questions, always ask. Okay. Now, before I get into the different syllabus for each of the days for the next 5 days or so, I have a little bit of anecdote to share. So Texas A&M, any of you know what the A and the M stands for? Why don't they call it the Texas University? Why they call it A and M? Any idea? Any of you know? So the A and M stands for Agriculture and Mechanical University. Okay. And it was set up in 1876. It started as Texas A&M College, and later on it became university. And it's a state university. It's not a private university. It was built with the money of the state government of Texas. There was something called Morrill Act, so the federal government of United States also gave money. And A&M is the only university which is a land grant, sea grant, and a space grant university, which means they have charter to help the society to advance knowledge in these 3 areas. Okay, in terms of land, in terms of space, and in terms of sea. I'll give you a hint. When was Industrial Revolution? It was early to mid 1800, right? And if you go back and if you look at the salary of a mechanical engineer in those days, and if you look at the salary of a doctor, a physician in those days, in today's money, it is $100,000 a year. Okay, there was a huge demand for mechanical engineers because Industrial Revolution had started. Electricity wasn't in that wide usage yet. In fact, it wasn't probably invented by that time, anyways. All the electrical machines had not come about, and so everything was steam powered. And guess what? Who does steam power? Mechanical engineer. You had steam governors, you had steam engines, all the industrial production, garments, you name it, was all powered by steam. Okay, it was all the thermodynamic principles, big demand. So somebody who knew, thermodynamics and how to handle thermal equipment was, sought after like crazy. Okay, and so 1876, 2018, that's how many years? About 132 years, 142 years. So in 142 years, the doctors kept their part of the bargain. In US, I guess doctors still get about $300,000 a year. I think there are very few mechanical engineers that make $300,000 a year. Okay, for doctors, it's more like a lower end of the spectrum, that kind of salary essentially there. But why should legislators invest and create mechanical engineers? What is the benefit to the MPs and MLAs in creating more? I mean, society benefits, of course, but how do the legislators, the politicians benefit if you produce more mechanical engineers? Any idea? If you were to take a guess, why were they interested in making more engineers? I mean, the General Electric, well, GE wasn't formed yet, but the companies, yes, they benefit if they get more mechanical engineers. They can improve their production, and the gross domestic product and the gross national product goes up. But how does it help the politicians? Can you take a guess? Anybody? So, where do politicians get their money to spend? Where do their incomes come from? How? Yeah, I heard somebody say a word. I was looking, tax, right? So, the more higher income population you create, the more tax it is for the legislators, and the more tax money they have, the more they can spend, right? So, that was their vested interest in starting the. The reason I am telling you all this story is Texas A&M is a very traditional university. It is a very old mechanical engineering program starting from 1870s. And so, when I started at A&M, and they of course want you to come up with your own research program, have your own niche, because you do not want to compete with a professor doing the work for 30 years. You do not want to work on a topic that somebody else is doing and is more experienced than you, because it will be much more difficult for you to get research funding, right. So, you have to find a niche where you can grow and prosper and compete. And so, when I said I am going to do nano, some of the senior faculty in the department got very concerned, because they thought nano was snake oil, and they thought mechanical engineers do not do nano, it is for chemistry and material science. Somebody with a thermal science background doing nano was very heretic. And so, constantly outside my research group as well as in my research group, I am answering these questions. Why am I doing nano? Not because it is in fashion, it has to be a scientific basis for doing it in thermal science. Okay. So, and so I encourage you to keep asking these questions while I am doing the presentation. Is doing micro nano in multi-phase flow justified? Because if you look at multi-phase flows, the history of it, the bulk of it got developed because of power plant technology development, okay, and the steam power development and so on. If I justify nano work, then the big question comes in: what type of nanoparticle should I use? Should I use carbon nanotube? Should I use silicon nanotube? And then where should I use it? If I take my refrigerator, for example, in my home, or the air conditioner, should I put the nanoparticle coating in the condenser? Should I put it in the ice box, or should I put the nanoparticles in the refrigerant itself? Which gives me the best performance, right? And then which nano manufacturing scheme should I use? I can use chemical vapor deposition, I can use physical vapor deposition. What type of manufacturing scheme should I use? But then the very fundamental question is: how nano should I go? Does a 1 nanometer particle give me better performance than 10 or 50? Where is that sweet spot? Okay. So, I will be presenting, at some point I will ask you this question: how nano from a multi-phase flows perspective makes sense? Okay. You guys should be thinking about it. Is a 10 nanometer particle better than 50 nanometers or 100 nanometers? Let us see if you can find it out based on the results that I am going to be discussing in this class. Okay. That is a design question. So, in terms of the contents, the first day we are going to talk about the introduction, the basics and convergence, and then we are going to talk about nucleate boiling tomorrow, and then the day after we are going to talk about flow boiling and convection. And I am also going to show you results where we did nanoparticle coatings, and we found that the flow boiling performance actually improved by almost a factor of 2. And in between, somewhere in between, I am also going to throw in a little bit of work we did in spray boiling. Okay. And then fourth day is more when we get deep into the special topics. We talk about the computational models, we talk about the boiling in porous media, and there is also a lab tour. Okay. And then the fifth day we get into the real core nanotechnology part of the multi-phase flows. Okay. Each day we are going to spend about an hour doing tutorials. I think that is one of the requirements for the Gyan course. That is how the course is designed. And so, this last 1 hour of every day we are going to be doing some problems, we are going to look into some discussion questions, and then on the very last day, the fifth day, you are going to have a quiz, like a yes no type of objective type of quiz that you will have to do, and then of course, you get your certificate for attending this particular Gyan class. Now, I will not spend too much time, how much when I start the day I am going to talk about the full details of what we are going to do, but so this is the structure for the 5 days. So, for day 1 we are going to start with convergence, this concept of that came out from National Academy of Engineering. I am also going to talk a little bit about the basics of thermodynamics of and heat transfer, particularly free and forced convection and transient conduction. And we are going to get started with the very first topic of two phase flow, that is the Young Laplace equation, which is the pressure difference between inside a bubble versus outside a bubble is 2 sigma by r. You all know that equation. Do you all know where it comes from? How many of you know how to derive that equation? Okay. Oh, great, I am impressed. So there are actually NPTEL also already has a few lectures where they actually do the derivation of this particular equation, but this derivation has a special significance when it comes to this recent topic of nanobubbles and nano droplets. Okay. People indiscriminately use this equation, this 2 sigma by r, for nano droplets and nanobubbles, and you cannot use it. Okay. This derivation of 2 sigma by r has some fundamental assumptions that is violated to nano droplets and nanobubbles, and people do not understand that, and that is where the whole controversy starts. So that is why I decided I am going to do the derivation once more, but this time I am going to explicitly make you conscious about where the assumptions are in deriving that equation. Okay. And then see if we can somehow modify it or extend it to nano droplets or nanobubbles. And this is of special, there is a big economic significance of this particular equation, and that is with respect to oil and gas exploration, particularly with respect to shale oil or what is known as tight oil. So I am hoping today, by the end of the day today, I will be able to address this tight oil question and this recovery of oil from shale rocks, okay, which is revolutionizing the whole world of oil and gas. The reason your oil prices have come down is primarily because of shale, shale oil. Okay. And so well, I am kind of getting ahead of myself. When we get to that topic, I will tell you some interesting facts that relates to the stock market actually. So in terms of my introduction, I am going to start with a little bit of a biography about myself, my research experience, then get into giving you an overview of all the research topics that we did in our research group over the last 13 years or so, and then I am also going to talk a little bit about some recent current activities, particularly my master's advisor, who is also a alumnus, Dr. Suman Sinha, and he is the son of Dr. GL Sinha, used to be the department head of mechanical engineering here, and to some extent this passion I have for commercializing research came from Dr. Suman Sinha. I learned it on sitting on his you can say feet essentially. So I will talk a little bit about the commercial impact of the work that we have done so far. It is basic fundamental science, but it has a lot of impact in terms of commercial applications as well. So talking about myself, oops, I went too fast. Yeah, this one has actually movies, so it might take a little bit to. So going back, as I mentioned, I was an undergraduate student here. So one time the hostel I lived here was Patel Hall, and one time I came across this book in our hostel library called Critical Path, and it was written by a person called R. Buckminster Fuller. Any of you heard that name? Buckminster Fuller. How many of you have heard that name? Okay. Any of you can tell me what you know about that guy? Nope, he did not. Carbon C60 was discovered only in the late 90s, and his peak of his, I do not know when he passed away, but I think he did not discover C60. C60 was discovered by somebody else, but he came up with that structure. Okay, anything else you know about this guy? Nanotechnology, nano wasn't a word in the 1960s. Nanotechnology wasn't even there when he came up with this buckyball concept. Any of you know anything else about Buckminster Fuller? So that C60 is called fullerene in his honor, because fullerene essentially. Any of you know anything else about him? No? Well, he didn't have a college degree. all right, but when man landed on moon, I think he was second or third in command for that particular endeavor. Sounds very interesting, right? So this is the day of Wikipedia. I wish I was a student on campus now. I go around the campus now and I'm so envious of you all, because when I was a student, Wikipedia wasn't there. I had lots of questions, I didn't know who to ask. These days you can just, your cell phone is your guru these days, you can find your answer right away, right? So you can look up on Buckminster Fuller later on, but I read this book Critical Path by, and he has a very interesting life history. I would recommend that you go back and read his biography. It's very inspiring, and he came up with concepts in cybernetics, he came up with concepts in history, and I think at one point he had the largest number of also. But when I was reading his book, this book Critical Path, there he argued that the future of mankind was in solar energy. Okay, our extreme reliance on oil and gas is kind of like burning your house to get the heat, because there is only so much of hydrocarbons that you have on earth, and if you extend your planning process to 1,000 years, this is not a very sustainable way to live. Okay, and so he argued that solar energy is the way to go, that we should be investing more and more of our resources in solar energy. So this was second year of as an engineering student when I read the book, and I got so enthused about it that that particular summer I did not go home back to Dhanbad. I stayed back and built a solar desalination still, just to learn how solar energy works. Okay, so my passion for research started when I was here, and of course my senior year BTech final project was on computational fluid dynamics. That's where my passion for getting into heat transfer and started. At the time I was looking into graduate school, there wasn't really much of a funding in solar energy, and I was thinking of doing my PhD here at IIT Kharagpur, and then one of my professors, Professor Shom, told me that whatever we had to give you, we have given it to you, now go out and see the world. Okay, so and I wanted to go work on solar energy, except that I couldn't find any program on solar energy, and so my mentors told me, well, if you want to get into solar energy, get into multi-phase flows, learn your heat transfer, at some point maybe the funding will come back. So off I went to University of Mississippi, did my master's work on artificial intelligence, and it wasn't a buzzword in those days, it was just one of those things you are doing. And then also I did work on flow separation on airfoils, and then subsequently I decided to move to UCLA and work on two-phase flows, boiling heat transfer. So in terms of my research experience, that's where it all started. That's where how I decided to get into a particular research area. And while I was at UCLA, I became fascinated with this new technology that was coming up called MEMS, micro electromechanical systems. Nano wasn't a buzzword yet, and I consider MEMS to be the grandfather of nano. Okay, the whole nanotechnology, the concept, and whatever enabled nanotechnology and nanofabrication was enabled by the technology of MEMS. Okay, how many of you have heard the word MEMS? Okay, any of you care to say what it is about? Yeah, but what is so great about it? Any idea? Go ahead. Yeah, sure, go ahead. So what is so great about miniaturizing mechanical devices? But why should I make a pump tiny? I want big pumps, right? Come again? Right. So there is a weight saving, material saving. Right, right. So you can see there is a savings in weight and materials. Is there any other benefit to miniaturizing thing? So I'll give you a hint. I have a big pendulum and a small pendulum. Which one swings faster? So what's the time period of a pendulum in terms of length? T equal to 2 pi root of L by G. So, if I make the pendulum smaller, the time period goes smaller, right. So, it goes faster. So, as you make things smaller, their actuation speeds go up. Okay. A big pump you cannot make it rotate at million RPM. A micro pump you can vary to million RPMs. Okay. So, there is benefits to going to MEMS, and so the biggest benefit you can think of is if you go back 40 years ago, the collision system, the airbag system in your car, that the detection platform used to be a box this big. It used to cost $80 a piece. Now it's on a silicon chip. It costs about $2 a chip, okay, because of this MEMS technology coming about, and it's much more sensitive. It acts faster. It's smarter, and so on. All right. So I became fascinated with MEMS. So I decided to do a minor, and so there was a MIT a startup company called Coventor. Somehow they found my resume, because I was actually thinking of coming back to IIT Kharagpur at that time, right after finishing my PhD. But I got a job offer from them, and I thought, I'm going to work with them for 2-3 months and then come here at Kharagpur. But life has different things for you in mind. But anyway, so that's where I started my professional life. After my PhD, doing MEMS and microfluidics, and in the process, I started working in. How many of you have heard this word, Human Genome Project? Any of you heard this word? No? Okay. So there they made this whole dictionary of the human genome. Our human genome is composed of several genes, and so on and so forth. And so they coded the whole human genome. And so as a mechanical engineer working in a biotechnology company was also a very interesting experience. So you can see I have had a very eclectic research background, both in terms of academia and then in industry. So my research group actually we work on a bunch of different aspects of multi-phase flows. Okay, and so incidentally, the human genome project ended 2 years ahead of time. They had originally scheduled 7. It actually ended in 5 years. Okay, and a big part of it was because of multi-phase flows. We could speed up the whole genomic detection because of multi-phase flows principles, applying it to the design and speeding up the whole analysis. So, so my research group, we work in multi-phase flows, both fundamentals and applications, particularly with respect to making these nano sensors, either nano thermocouples or nano diodes. You can use a diode as a temperature sensor. That's where we first discovered that on the nanoscale there are some fractal features that are happening. We also work in thermal energy storage. You can think of a thermal battery. When you buy a battery in the store, what are the things you care about? You care about how long will the battery last, right? How much power can I get out of the battery? And if it's a rechargeable battery, how many times can I recharge before I have to throw it away? The same concept applies to thermal battery. What is the power rating of your heat exchanger? How much power heat can you get out of it or get into it? How fast? How long will this thermal battery last? And how many times can I recycle before I have to throw it away? So you can do either with phase change materials or PCM, or you can do it through a chemical reaction, like in a battery. Okay, so that's thermochemical energy storage. And then, of course, going back to my industry background, we also do a lot of micro channels, microfluidics, and but I got into nanofluids, these nanoparticle additives, by accident. I worked at Air Force Research Lab for 2 summers, and my whole we are also looking at using microchannels and nanochannels for biotechnology applications. And then going back to my experience doing CFD, starting with CFD at IIT Kharagpur, we also have a lot of numerical work that we do in our lab with respect to finite element, computational fluid dynamics, and recently we have started doing some molecular simulations as well. So all this work wouldn't have been possible unless there was resources available. So these are the different sponsors, from the federal agencies, from the state agencies, from the state of Texas. Texas A&M has a campus in Qatar, in Doha, and so we get some funding from Qatar also for doing research in our lab. And then a big part of what we do is also industry funded. Okay, so in terms of the industry funding, I think these words are a little small. I apologize for those of you sitting in the back, but we did a lot of small business grants, or what are known as SBIR in US. Okay, where we worked with companies in developing products. And then, of course, I am not a genius. I rely on the creativity of my students, but I also rely on the help and advice from multiple collaborators, both in national labs, in federal labs, and then of course across different universities in the US. So, and then a big part of the discovery we did with molecular simulations was funded by this consortium called the DARPA Micro Nanofluidics Focus Center, or DARPA 3. So, this was a consortium of 12 universities, about 20 faculty, 8 companies and 2 national labs. So, they are all listed here. I won't bore you with naming all the names here. And then in terms of the different types of projects that we have, I have listed it over here. So, the Gyan course that we are going to be discussing is primarily based out of these particular projects that are highlighted with these red arrows, both in terms of nanostructures and nanoparticle additives, and then in terms of the micro and nano channels essentially. And so, as I mentioned, technology commercialization is a big passion of mine. Aspects of what we are going to discuss here are also there in that ASME course. Okay. And so, just as a teaser, okay, why should we care about these recent topics in multiphase flows? So, when it comes to putting nanoparticles in coolants or oils, okay, how much time do I have? Okay, all right. So, think about this. Oils are typically used for cooling, right? You cannot use water all the time. There are certain sensitive applications where, particularly with respect to electronic chips and things like that, where you cannot use water. So, you typically end up using organic liquids, either refrigerants or oils to do the cooling, all right. And typically, if you look at the heat capacity, water has a heat capacity of watts per meter Kelvin, and then there are these exceptional solids like copper, where you can go up to as high as 400. Okay. So, the general thinking was, if I mix some solid particles with my oil, my thermal conductivity will go up, but I will sacrifice my heat capacity, right, because I take a oil which is 2 joules per gram Kelvin, I take a solid which is 1 joules per gram Kelvin, I mix the two together, then it should go down, the mixture heat capacity should go down. So, I am sacrificing my heat capacity, but I am getting more thermal conductivity. Okay. So, I am improving the power rating, but I am decreasing the capacity of my system, okay, thinking of in terms of electrical battery. But when I for research lab, we were mixing these nanoparticles with oil, and the heat capacity went up by 50%. Okay. The first time we did it with graphite nanoparticles. The next summer I went back with another student, and we did the experiment with carbon nanotubes, and it jumped. And we were putting nanoparticles at concentration of 0.6%, not even 1%. It is like taking a beaker of oil, putting some pixie dust of nanoparticles, mixing it together, and then the heat capacity has jumped by 20 to 50%. How do you explain that? Okay. I am not asking you to explain it right now, but that was the first shock that we got, that when it comes to this nanoscale multiphase flows, there is something else that is happening that we did not think in a conventional sense. Okay. Now, in parallel, we were also doing boiling experiments in our lab, and we were making carbon nanotube coatings on a silicon wafer, putting it on a heater, pouring refrigerant and boiling the refrigerant off. Okay. And we found that when you put the nanoparticle coating on the heater, the boiling heat flux, or what is known as critical heat flux, goes up by about 60%. Okay, no surprise there. Nanoparticles, and why we put nanoparticles, I will come to that a little later, justification for it. But let's just assume it was in fashion, funding agencies were giving money, so I did it. Okay, that was not the story, but anyway. Now, we were not really sure where the the improvement in boiling was coming from. So, we made silicon nanoparticles and did the same experiment with silicon pillars or silicon fins etched on the silicon wafer, made nano fins, right. And which one do you think has a higher thermal conductivity, carbon or silicon? Any idea? So, think about it, in your cutting, when you do metal cutting, what type of particles do they put in the cutting fluid, do you know? They put graphite particles, because carbon has a very high thermal conductivity. Silicon actually has a lower thermal conductivity, but to our horror we found silicon was producing double the amount of vapor than carbon. So, a lower thermal conductivity nanoparticle was giving us more boiling heat transfer. Okay. How do you explain that, right? And so, when we teach undergraduate heat transfer, higher thermal conductivity means higher heat transfer for the same temperature drop, right. So, something weird is going on, right. So, and then we repeated this same experiment, the boiling. First we did pool boiling, then we did flow boiling, and when we put carbon nanotube coating, of course, the heat transfer went up by a factor of 2. Okay. And then, as I mentioned, we were the first to do fin boiling experiments as well, and to my knowledge, we are the only one who has done it, because doing fin boiling experiments is not that easy. Okay. And we found the height of the nanoparticles also became an issue. So, if your nanoparticle height is below a certain number, you do not get any enhancement in film boiling. In nucleate boiling, you do. Okay. In film boiling, what it happened in Chernobyl was the whole control system collapsed, and there was a blanket of vapor that formed on the top of the heater, and the blanket is a very low thermal conductivity material, and so the whole thing melted, right. So, it turns out when you get into film boiling, the height of those nanoparticles also makes a big difference, okay, and that we could predict from our computer model, and so that's how we designed the experiment. But so there are a lot of counterintuitive things was happening when it comes to boiling. And then one of my students went back and worked with the same group I had worked at Air Force Research Lab, and they did spray cooling. And what they found was when they put nanoparticle coating on the heater, the boiling heat transfer went up by a factor of 6 to 8 when it came to spray cooling. Okay. Very counterintuitive results. All right. So, how do you explain it? So, I am kind of giving you the story, the end of the story at the very beginning. It is a suspenseful novel, right. So, I should keep you hanging until Friday and then tell you the answer, isn't it? But and I am not trying to peddle my book here. Actually, we just got an honorarium of $500, and this book 70% of the, I mean, Navdeep, who was my PhD student at that time before he joined University of Houston, that we were seeing. Okay. And what we found was it is not what is happening in the nanoparticle itself that is the problem. It is at the interface between the nanoparticle and the fluid is where the whole game is going on. Okay. So, the dynamics at the interface between the solid and the liquid is what is controlling the game. Okay. So, you have a resistance at the interface between the solid and the liquid, or what is known as interfacial resistance. And more interestingly, when nanoparticles have very high surface energy, because they have a very high surface area per unit volume, because when you shrink an object, the surface area goes up faster, per unit mass, right. So, because they have this huge amount of surface area, they were absorbing a lot of the fluid molecules on the surface. Okay. So, that surface adsorption acts like an energy storage, it's a capacitor. Okay. And because there is a high density of surface, because of surface adsorption, the density of the fluid molecules on the surface actually goes up dramatically by a factor of 2. Okay. So, now you have created a density gradient from the surface of the nanoparticle to the bulk of the fluid. And so, because of that density gradient, you also get what is known as a thermal diode. Okay. And what does it mean to have a thermal diode? Just like you have electrical diode. In electrical diode, when you change the positive and the negative terminals, in a resistor, whether you change the positive and negative terminals, it does not matter, you will get the same current, right. But in a diode, when you change the terminals, it goes down by a factor of 10, isn't it? When I connect one end to positive and one end to negative, let us say I get 1 amp. When I switch a diode, the current goes down by a factor of 10 to 100. So, we also get a very similar effect. We get a thermal diode at the interface, and so the combination of this resistance, capacitance, and diode is what we call as the nanofin effect, and so that's what you see is denoted by that schematic diagram over there. Okay. So, hopefully by the end of this Gyan course, you will I would have explained to you where all these 3 features come in, for the nanofin effect. So, let's see, I can skip these parts, So, should we take a break and then come back for convergence, or should I think let's take a break and then I will start with this big picture overview of what we mean by convergence. But just as if you look at your cell phone, it's a great example of convergence. There are so many technologies that got in, right? There is a camera, there is a speaking, there is internet, Wi-Fi, right? And there is all information processing, there is a cloud computing. So there are so many things that came in onto that device, but that's not what convergence is. Okay, the word convergence or this concept of convergence is much broader than what you see in a cell phone. A cell phone, I would say, is a version of what convergence people are thinking about. Okay, so more on that after we take the break. Okay, all right. Any questions so far? Or we can discuss it over tea. So, for this next 1 hour, my plan is to talk about convergence and then go over some of the basics of heat transfer and thermodynamics. And then in the afternoon session, we will spend about an hour going over nanobubbles, nanodroplets, shale, tight oil application to nanochannels. Okay, and then we will have 1 hour tutorial, and that will be the end of the day for today. Okay. So, talking about convergence. So, I was talking, if you look at the cell phone, there are so many different technologies that got into it, right? And now you have this finished product in hand, and it's revolutionizing society in multiple ways. Places where they don't have electricity, places where they don't have doctors, they're able to use the cell phone and still get a remote diagnostics done, right? So that is the basic concept of convergence, that you combine so many different technologies together that it has impact on society that was not possible before. Okay. So, but what is convergence really? Cell phone is not really an example of convergence. Okay. Convergence as a concept is a much broader concept. And now, why am I talking about convergence in multiphase flows? Because I think multiphase flows has so long been treated as a very academic, very specialized subject, but I think it has capability to transform society in multiple ways. If we are aware of this concept of convergence and if we can leverage it, I think our impact of what we do as a community of multiphase flows researchers, our impact will be much far reaching. Okay. So, that was one of the reasons I decided that I will talk to you about convergence. This thought process, I am trying to influence your thought process. So you are more aware of what the impact of what you do, and or to leverage the impact and increase it in a much wider way for society. Okay, that's the whole idea behind discussing this topic. I could as well have skipped this topic and just gone directly to multiphase flows, but I think that way we are underselling ourselves. We are capable of doing much more than what we do right now. So here is a good example, in terms of how technology has evolved, right? So cell phone doesn't have tail anymore, like your regular phone used to have. And a more example that is there now is this concept of cloud computing, right? So you all are aware of what is cloud computing. So can somebody tell me what is cloud computing? Go ahead. Come again. Is it just Google Drive? Okay, so is cloud computing just storage, or is it more than storage? Okay, so what else is cloud computing doing that your thumb drive or your CD could not do?
Your programs can run on many servers.
Right, right. So So you are leveraging not only the memory, but you are also leveraging the computational power essentially. Okay. So what enabled the cloud computing? Why was cloud computing not possible before? Internet has been around for such a long time. It's only now that cloud computing is happening, right? So what enabled it? Can you all think about it? Any idea what enabled cloud computing? Come again?
Somebody says security.
Well, I guess security standards were there before also. I mean, yes, security is one aspect of it, but what was the key defining feature that enabled cloud computing to happen? Right. No, so that was there 20 years ago also. Internet was there 20 years ago, so you could have access from anywhere. You all heard about this word called data centers? What are data centers? Any idea? So to you, what does data centers mean? Come again? So I can have a server in my home versus one of these big companies has a server. What's the difference between the two servers? Okay, so now you have a dedicated warehouse filled with computer chips, right? And all they are doing is they are doing data crunching all the time, essentially, right? So to a large extent, there are these key enabling technologies that lets other technologies expand exponentially, right? So these are sort of mini examples of convergence. So I'll talk about so I've been so long I've been telling you what convergence is not, right? So but what is it really? Okay, so one way to illustrate it is to illustrate it through the example of life sciences. Okay, there is a lot of different technologies that are coming into life sciences that are enabling it. Okay, and so for convergence to happen, you need an ecosystem of communities, of infrastructure that has to come together for it to be really successful. Okay, and I'll end with terminologies. So you have something called multidisciplinary, you have something called interdisciplinary, and then you have convergence. Okay, so how are they different from each other? These three terms. That's what I'm going to wrap up with, and this is a food for thought. Think of how you can maximize your impact to society as an individual human being. Okay, otherwise we just eat, sleep, go home, come to work, and that's it. Is that what we as human beings are supposed to do, or is there a bigger purpose in life, right? And so that's where this concept of convergence comes in, where we as individuals have a bigger impact on society. Okay, so so I guess this is a very good example of what a convergent technology could be, if we could tap into our dreams and send emails in our dreams, essentially, right? So so think of a cell phone that's connected to your brain, that your thought processes are getting transmitted without you ever having to speak, right? So the consequence of that would be, when you are dreaming, your cell phone would still be sending messages, right? So what is convergence? Okay, so let me give you a very verbose description, and then I'll give you a more condensed definition of what NAE thinks, National Academy of Engineering thinks convergence is. All right. So convergence is outcome focused, okay, and it crosses boundaries, but so does interdisciplinary research or multidisciplinary research. Now the difference of convergence compared to the other terminologies of interdisciplinary or multidisciplinary is, whatever is the parent technology that you are putting together to come up with this new thing actually goes back and affects the parent technology. Then it is a convergence. If it doesn't affect where the parent technology came from, then it is just multidisciplinary or interdisciplinary research. But the fact that you have created something new that goes back and affects the source is what convergence is. Does that make sense as a concept? Okay. So if you think about cell phone, there was internet that came along, right, and there was voice communication that came along, right. But the moment you put this cell phone together, you put it in a cell phone together, it actually went back and affected the protocols of both of these technologies. Both of these technologies had to evolve in order for that convergence, because that convergence happened. Does that make sense? Okay. So, so in other words, the idea of convergence is to push basic research to broader goals to meet certain societal needs. Okay. So there are many research questions that require multiple disciplines. So if you are doing computational fluid dynamics, you need to know fluid mechanics and you need to know computational methods, right. So that's interdisciplinary research or multidisciplinary research. You need expertise in both your numerical methods and you need your expertise in Navier-Stokes equation in order for you to do CFD, right. But that's not convergence. Okay. But if I am planning a whole computational architecture around a particular problem, let us say I have to deliver a medical information to a remote village, for example, and I develop the technology that makes it possible, then it is convergence. All right. So, and a big part of this convergence happening is because universities have decided to get into the commercialization business. It is not just publishing papers, but making something out of it that will benefit somebody else outside the university. Okay. So, so if you look at the stakeholders across the ecosystem of convergence, it includes government, it includes foundations, it includes industry, it includes academicians, it involves scientists, clinicians, practitioners and so on. Okay. So a good example is this brain initiative at Harvard University that's been done by this institute, research institute called Weiss Institute, where they are bringing in computer science, they are bringing in electronics, they are of course bringing in doctors, and not only are they tapping into the human brain and understanding how the human brain works, but it is also affecting the sensor development that the engineers developed in the first place to get into that project. So, the whole paradigm of thinking of how you design sensors is also changing, because there is this challenge of we need to understand the brain. Okay. And so, I am very proud to say that IIT Kharagpur is also actually one of the pioneers in this convergence thinking. So, there is a new petroleum engineering department that has been started here, and they are not calling themselves just petroleum engineering, they are calling themselves transdisciplinary program in petroleum engineering, TPPE, okay, which means they are thinking much broader than just making petroleum or extracting oil. Okay. Because any sort of energy activity that you do also has an impact on the water resources of that community. Okay. So, the original thinking of petroleum was, okay, I got to go drill, take the oil out. Okay. But a transdisciplinary program is not just thinking of oil, but it is also thinking of water. Okay. And so, the graduates that are coming from that program are not just focused on drilling and production, but they are thinking of a broader question to society in terms of what do I do with the produced water, how can I make my water resources more go a longer distance essentially than it currently does. Okay. So, that is a good example of what a convergent way of thinking. So, in other words, a convergent way of thinking is to take a problem. So, think about your undergraduate days, right. You came in, you learned fluid mechanics, you learned heat transfer, you learned controls, you learned manufacturing. All right. So, that is a multidisciplinary way of building an engineer. Convergent way of building an engineer would be the engineer comes in the first year and they are asked, you have to go make a refrigerator, okay, on the very first day. So, now this guy has to think, okay, in order to build the refrigerator, what do I need? I need to understand controls, of course, I need to understand fluid mechanics, heat transfer. So, it is a different approach altogether in terms of developing the new class of engineers. Does that make sense? Okay. So, you are working on yourself, you are developing the skill set around a problem rather than developing the skill set first and then going and solving a problem. Okay. So, it is a different way of thinking, it is much more applied, much more hands on. So, and the problem can be in fact broader than that. You have to make a refrigerator and sell it. Okay, if I pose that as a problem, now this student also has to think of finance, has to think of entrepreneurship, right, has to think of economics, right, and we as engineers, at least when I was getting my engineering education, I didn't think of that I have to sell a mechanical product one day. My thought process was I get my degree, I get a job, right. So that's a multidisciplinary way of thinking, but the convergent way of thinking is not just making the product, but how it fits into the society. Okay, that's the convergent thinking. Does that make sense? So when we are talking about multi-phase flows, it's not just the equations, it's not just the theory, but how do all these multi-phase flows fit into the broader needs of society. That's what I want you all to think as a part of the Gyan course. I'm hoping that's the thought process I permeate into you all at the end of this course. Okay, that your outlook is much broader than just the equations in a book or a paper. All right, does that make sense? And if you disagree with me, please feel free to let me know during the break. All right. So now that I gave you the verbose description, let's look at the succinct definition, and this is how the NAE document defines convergence. So convergence is the coming together of insights and approaches from originally distinct fields to create scientific opportunities and technological breakthroughs as well as inventions. Okay. So convergent science fields provide a starting point to organize around compelling scientific and societal challenges. It's not just a technical challenge that you are solving, but you are also solving a societal problem. Okay, that's where convergent thinking comes about. All right. So if you want to read about this, this is a book that's available for free. And by the way, I don't know if they got the
no, not yet.
Not yet. Okay. So all these slides you will get it. It's already uploaded to a file sharing site. It will be, that link will be mailed to you today, and so you can download these slides. And then I have a bunch of handwritten notes because I hate doing death by PowerPoint. Okay, I can show a bunch of PowerPoint slides to you all, but at the end of the day you become zombies, right. So I'm more in terms of I prefer writing it on a piece of paper and projecting it. So all that things that I'm going to write over here, I already have those handwritten notes. I teach a two-phase flow class, so all that handwritten notes are there in that link. You can download those PDFs, and I give out a bunch of handouts as well in addition to the handwritten notes. So we are going to talk about wave theory, right, traveling waves. So if you have not taken a course in physics on traveling waves, I have a few handouts in that zip file. There are a bunch of PDF files. So there is one of the handouts that talks about the concept of traveling waves and the basic physics of traveling waves, for example. Okay, when we talk about instability theory, so all those are there. You will get it today. All right. So in fact, this the reason I'm saying this is the report on convergence, and so that was published in the National Academies Press, and that's the DOI number, and you will get it in the PDF file. You don't have to write it down, but if you go to any online search, and I'm explicitly not mentioning a name, you can see that. So any online site, search engine, if you give out the DOI number, and there is another way to access DOI. If you have a DOI number, you can access the PDF. Do you know how to do it? So there is a website called dx.doi.org, and if you go and just type that number at the end of DOI, if you go and type in that number, it will pull out the original link for that paper essentially. Okay. So if you type in that in the dx.doi.org, you will be able to get, or you can go to National Academy's website and you can download the PDF for free, and it's I guess a 300-page document. They do a lot of discussions. It's very insightful, and the first time I read it, I was very excited, because it's a completely different way of thinking about what human life should be. Okay. So so how will you enable convergence? Okay, it's a mindset. Okay, so it's an entrepreneurial mindset. It's not I get my degree and I go work for a big giant company. No, it's a different. It's a whole way of thinking about yourself as a person, how you fit into the rest of the society. So it's a different mindset essentially, And so what will enable convergence? Well, so it will entail partnerships at the intersection of the life and medical sciences, physical sciences, computational sciences, and engineering, as well as economic, social and behavioral sciences, arts and humanities disciplines and beyond, okay, thereby amplifying the potential for innovations of incredible variety and magnitude. Okay. So, so it's a mindset really, and so what this NAE document is trying to do is trying to change the mindset of engineers and science majors and math majors in terms of how they perceive their future role is in the society, okay, as they grow up. So, one good example is in the life sciences community. Okay. So, talking about enabling technologies. So, in 1953 the structure of DNA was discovered. Okay. A woman scientist discovered it, but somebody else got the credit for it, Watson and Crick. Somebody else had the X-ray crystallography information, they looked at it and immediately became clear to them it is a double helix. Okay. Unfortunately, she died, so she never got the Nobel Prize, but she was the one who deserved it really. And so, there was this DNA structure was discovered, and then there was also the revolution in molecular biology in terms of how proteins interact with each other. The protein was one part of that puzzle, DNA was one part of the puzzle, and when these two techniques came about along with different engineering technologies, multi-phase flows happens to be one of them. That is the technology of microchannels, flow in microchannels. Okay. So, once this microchannel flow became widely popular, that actually served as a vehicle for these things to come together. Okay. And so, if you look at the timeline in 2009, based on the discoveries in 1950s and mid 1970s, National Association Academy of Science, they came up with a report just like this convergence report. They called it a new biology. Okay. And that plus the Human Genome Project, and that actually enhanced our understanding of how genes work and how proteins are made, and that led to a revolution in terms of how new drugs are discovered and how new drugs are made. Okay. So, one example is when we make silica, how do we as engineers make it? Silica is what? Glass. So, how do we make glass? So, what is glass made from? Any idea? Where does glass come from? Sand, right? So, how do you make glass from sand? You heat it. But if you go look at these diatoms, these tiny creatures in the ocean, they make silica glass too. They make it at room temperature. How do they make it? Okay. And so, there is a whole biotechnology topic in terms of protein pathways. They use proteins to make silica, they do not need to use heating, it is just simple chemical reactions, right, but they make these wonderful structures in the ocean, the diatomaceous structures, essentially it looks like powder basically. Okay. And now, why do I care? Because it turns out those diatoms, the silica that is made by the diatoms are very porous glass, and they are very good candidates for drug delivery. You can soak it in a drug and inject it. Okay. So, you can see a marine biologist is affecting how drug delivery is occurring in human beings. Okay. So, there are technologies that are being developed in totally disparate fields that come together and creates a impact on the society. Okay. So, the convergence ecosystem in terms of who are the players here. Okay. Of course, there is industry, there are academic researchers, there are government policy makers and government researchers. And then if you look in terms of the disciplines, you have the computational people, the information scientists, so to speak. There is physics, there is engineering, there is medicine, there is chemistry, there is biology, right. So, you can think of it in terms of the vertical structure, and then you can think of it in terms of the horizontal structure. That is the ecosystem that you are dealing with. Okay. And so, these days A physicist cannot just say I am just going to look at the laws of relativity and that is it. A physicist has to learn computational techniques. Okay. Engineers have to worry about information theory. Okay. As we as mechanical engineers, at least the next generation of mechanical engineers we produce, have to be aware of what information theory is. Okay. We can no longer be just working on gears. Okay. So in other words, you have to develop these multiple skill sets and multiple ways of looking at things. Okay. So if you look at the convergence ecosystem that led to these breakthroughs in medical research, there was biomedical research, there was clinicians, and then of course there you have electronic health records, you have basic science discoveries, there is information technology also coming into play, and all of these things actually play a very key role. You cannot leave one from the other, and that whole thing will not work. So to wrap it up, what is convergence? Well, it is not multidisciplinary research. Okay. Multidisciplinary is when two or more disciplines are focused on a same topic, okay, but the disciplines remain separate. All right. The existing structure of knowledge is not questioned, and the teams work separately. All right. Now, when you look at interdisciplinary, in interdisciplinary you are integrating information, techniques, data, tools, concepts from two or more disciplines. So you are generating a new conceptual framework and a dynamic communication between team members. So if you think about it, and I guess Dr. Bhattacharya can actually tell you more about this. In the early days of Intel's chip development, the chip development used to happen first, then it used to come to the thermal engineer to decide what size fan you want to use to cool it. Okay, that was multidisciplinary research. The interdisciplinary research is where when the new chip is being developed, they have a thermal engineer on the team from day one, okay, to make sure that the team is going in the right direction. Actually, one of my good buddies from my IIT Kharagpur days was working for HP, and one time I asked him, how is your experience working at HP as a thermal engineer, and he said, well, sometimes I feel like a janitor. And I said, what do you mean? So he said, well, the electronic chip designing team makes all the mess, and then they give it to me to decide how to cool that chip, but by the time it comes to me, it is already a messy situation. It is a lost game because it is dissipating a lot of heat, but if they had originally thought about it, they could have prevented a lot of this mess from the very beginning. Well, it does not happen like that anymore. Now if a chip design team gets in, they make sure there is a thermal design engineer on that team to make sure they are going in the right direction. Okay, that is what interdisciplinary is. All right, but that is not transdisciplinary. Okay, so transdisciplinary, or what is known as convergence, is something that transcends disciplines. Okay, you have a thermal engineer who already knows about IC design, okay, or a IC design engineer who already knows about heat transfer, essentially. Okay, so a good way to think about it is you want to eat fruits. Okay, let us say you want to have watermelon and you want to have mango. Now you are trying to decide whether I want to have the mango first or the watermelon first. Right, that is multidisciplinary. A fruit salad is an interdisciplinary because you have cut up the mango, you have cut up the watermelon, you have mixed it together. Okay, but they are still distinct. A fruit smoothie, in contrast, is transdisciplinary because you cannot separate one from the other. You have taken them together, you have made a smoothie out of it, and now it is one homogeneous whole, okay, where everything is integrated together, you cannot separate one from the other. That is transdisciplinary. Does that make sense? Okay. So with that, let me stop about the convergence. So our original thinking, the way we built engineers or scientists, was about a bunch of different disciplines, and then you have a depth in one discipline, multi-phase flows. Okay, about heat transfer, about controls, about manufacturing, but you all are doing your thesis in multi-phase flows, right? A transdisciplinary approach, on the other hand, is more like a comb than a T, where you do not have a depth only in one subject, you have depth in multiple subjects. Okay. So, which means actually a lot more work on your part as a citizen of the society. Now you got to know more. Okay, so you cannot just survive just by knowing a whole lot about only one subject. You have to know about multiple subjects. All right. So, a good example, this is a Stanford University. They did a map of how different professors and research groups interact with each other, and they came up with this concept called BioX, where they are trying to answer questions in biology and life sciences. Okay, and they are nucleating all the researchers who have interest in this particular topic around it, and they did the map after BioX was formed, and you can see things have become like a fruit smoothie. Okay, it's very difficult to distinguish these connections run from each other, versus the diagram on the left. You can very easily figure out which groups are where in this network. Well, after BioX was formed, now this network model has become much more dense. Essentially, it's very difficult to distinguish one from another. So, so think about this. I don't have all the answers for you. This is a up and coming way of thinking about life, about society. So, what is enabled by convergence? Okay, what are the challenges? If you do want to build up the convergence ecosystem, anything new has an activation energy, right? You have to go through that activation energy bump. So, what are those activation energy bumps? What are those challenges that you have to go over? What mechanisms can be used to support and facilitate convergent research? Does it mean having mechanical, chemical, electrical in separate parts, or do you want to do it like Apple, where you have a building that looks like a space saucer, right, and everything is integrated in that building essentially? Is that feasible? And what are the challenges to implementing convergence effectively? Okay, and so the key is innovation, thinking about things in a new way. And so let me take a brief break here. We are not going out, but are there any questions, any thoughts? Now that we have discussed this concept of convergence and transdisciplinarity, what are your thoughts? I am curious to know. What are your reactions? I don't want to do all the talking, I want to give my vocal cord a little rest. Any thoughts? Do you think it's a ridiculous idea? Is it the language Pascal that will never survive? Anybody heard this computational language called Pascal? You know of C, you know of C++, right? How many of you have heard the word Pascal? Any of you used it? I used to love that language. If you wanted to program in Fortran, I'm talking about the time of floppy disks. You needed 5 floppy disks. There was no hard drive. You had to put your floppy disk, you had to put your other floppy disk and do your coding, and you had to carry your operating system on a floppy disk. And if you had 5 floppy disk operating system, you had to exchange every 10 minutes. It would say insert disk number 2, and you insert it, it does the next computation. I loved Pascal because it used to come in 1 floppy disk. If you did graphics, 2 floppy disks. The whole operating system used to fit on a floppy disk. So, if you had a 2 disk computer, you put the operating system in one, your program in the other, you are good to go. But that language never survived. I don't know why. I was too young to know the nuances. But maybe convergence is Pascal. It's a great idea. It works great, but the adoption wasn't there, or somebody else came up with a better competition, or maybe unfair competition. Who knows? So, I don't know if this is going to fly. It's a new concept. It's a 5-year-old concept. 20 years from now, we will know if this concept was a good concept or not. But what do you think? What's your reaction? Who are the KGPites over here? Can you raise your hand? So, I'll put you guys on the spot first because you are local. Particularly because petroleum program here has already started it in their curriculum. So, yeah, go ahead.
So I think it's a good concept because especially in the undergraduate course, the students are taught a lot of subjects, and especially it's a theoretical base. With the help of this concept, if it can be applied to the ground level, then the students will be much more product oriented. They will learn much more product oriented.
Right.
And number 2 is that the entrepreneurship. compared to US,
Mm-hmm.
that entrepreneurship and the creativity environment in our country could be developed if it is implemented in our country.
I disagree with you on one thing though. I think India is very entrepreneurial. Maybe not in the high tech space, but if you think about the person selling tea, right? Right. So no. So entrepreneurship doesn't necessarily mean making the next IT company, right? That's entrepreneurship too. So I think India has more entrepreneurs than any other country if you think about it in that way. It's just a question of what product are the entrepreneurs on. Is it regular mundane products or is it the product of the future? Yeah. So if it comes to entrepreneurship in developing products of the future, maybe India needs to do a better job. But I think we have more entrepreneurial people here than anywhere else. Maybe China, who knows? So, but I do hear you. So as a professor, when I teach a new course or when we are teaching fluid mechanics, and I'm teaching Navier-Stokes equation, oftentimes I get the feedback from students, why am I learning this? Or the first year student, doing the numerical methods class, they are thinking, oh, these are just mathematical algorithms. But the broader picture is lost, and I think only when you get into the third year or fourth year of your undergraduate studies, then you realize, okay, things I learned in first and second year, what is the impact of that, right? That realization comes in much later. But with a convergent way of thinking, you are aware of the impact of what you are learning very early on, right? Yeah, that's very true. So I agree with your comment in that regard. Okay. Sure. Right. Mm-hmm. Right. Right.
Nowadays we are facing a different kind of set of problem.
Mm-hmm.
Nobody wants to join the core branches. The students they qualify JEE, main JEE.
Mm-hmm. Mm-hmm.
Everybody wants to join the IT sector.
Right. Right.
And they are looking on one thing, that what is the kind of pay packet I will be getting after graduating from the institute.
Right.
They
Right.
are not at all interested.
Mm-hmm.
They are mechanical, not electrical.
Right. Right. It's what kind of job will I get?
I mean, this concept which you are telling, that they just want to take the degree.
Right.
And they just want to earn.
Mm-hmm.
Nothing else they want to do.
Right. No, so I mean there is no harm in being very earning focused. So, but
No, when you take the fundamental courses, they are not at all interested.
right.
So what you are telling, that is already there in the books.
Right.
And
Right.
it's much more vigorously written and explained in the NPTEL side.
Right. Right.
They don't feel like coming to the class. I mean, this is the problem which I am facing as a faculty member.
No, and I wouldn't say it's just NIT. I think I see it in the US universities too. The students.
A lot of convergences you are talking of.
Right.
These terms are unheard of in our institute.
Right. Right. No, so it's true in US too. I get a bunch of students who are just looking to get the degree so they can go and join an oil and gas company. We are close to Houston, and so oil and gas jobs are sought after. A good majority of our students are thinking, I need to graduate so I can go for an oil and gas job. And so I don't think there is harm in the students being earnings focused or jobs focused. I think that's part of the process. How much time do I have?
20 minutes.
Okay, I'll do the basics, the heat transfer basics after the, I was planning to do it now. Now the reason is, that's where the role of a teacher comes in. So I think there is a fable in India which illustrates the concept of a teacher very well. Okay, so convergence is not about teaching. Convergence is about a mindset, about realizing how I fit in with the rest of the society. That's what convergence is. Okay.
So instead of teaching the basic courses on physics, mathematics, and chemistry, they should teach this approach first. And when they come to the institute, when they join the institute,
right.
What is expected out of you?
So instead of doing the final, all engineering students, I guess, do a final year project, right? So maybe the student should be starting with the final year project in the very first year. You have 4 years to build this and sell it. Okay, so there is a college in US called Olin College. Any of you heard the name? It's a very entrepreneurship focused engineering college. They don't have graduate programs as far as I know. They are only doing undergraduate programs. And so a few years ago I was in BE College, Shibpur, which is now I guess now called IIEST, and I was having tea with a few of my buddies from my undergraduate days. They are faculty now there, so I usually go have tea with them, coffee with them once in a while. So one day I went to visit them, had coffee. I was coming back, and I noticed a bunch of students from US on their campus, and so I kind of got curious and I started asking, what are they doing here? Turns out they were students from Olin College. So their project was to build a hand pump that people who are in the slums can use. Okay, so that was their engineering project, the so-called final year project. And so they were here in Calcutta to go visit the slums to see how people live there, because they didn't want to design a pump that's alien to the lifestyle of the people who are going to use it. So the first thing they wanted to go do was go into the slum, see how the people live, how they make their living, and then conform their design around their way of life. I mean, they could be sitting in the US, design the best possible hand pump out there, the cheapest one, but if it does not meet their needs or their way of lifestyle, the whole process will be worthless, right? So another good example is there is a guy called Brian Wilson, and he has come up with this fuel efficient chula, oven, and they came up with a very nice alloy that was cheap and very durable, with which they could make their burner, and it was supposed to reduce the pollution from burning the coal by like a factor of 10, but within a month it started failing. It never failed in their lab, and so they came to investigate, and they found that whenever somebody gets a new chula, they burn milk on it. That's the tradition custom to get a new chula started, right? You do a prayer, you burn the milk, and turns out when they were burning the milk corrodes that alloy. In the lab they never tested whether they tested it for corrosion with coal but not with milk. Okay, so now you understand why the people from Olin College came to visit before they did the design, right? And they had a constraint not only in terms of performance but also in terms of cost, because at the end of the day these people living in the slums will have to buy it. Okay, so I think Olin College is sort of getting on that convergence bandwagon, even though they are not probably very explicit about it. Does that make sense what I am saying? Okay, so it's a mindset really, and so that's where the concept of teacher comes in. That's why I'm sacrificing a part of the lecture, because I want to tell you a story. Okay, so I can tell you the source of the story, but then it will get into a religious context. I don't want to get in there, but the story goes something like this. So one time there was a tiger, and the tiger gave birth to a cub and died. And so as this baby tiger, the cub, was roaming around, it got into a herd of goats, and so it grew up like a goat. Okay, it bayed like a goat, it ran away whenever it saw a tiger, and so one day another tiger attacks this herd and sees that there is this fully grown tiger that's running away with the rest of the goats, and it's baying like a goat. So he got very curious. So he caught hold of that tiger, this adolescent tiger, and brought him to the pond and said, look, you are a tiger, I am a tiger. And this guy would still not accept it. It gave it a piece of meat and it wouldn't eat it because it wants to eat grass. Okay, so sorry, I told it the other way. So it gave it a piece of meat, it wouldn't eat it because it was grass. So finally it takes it to the pond and says, you are a tiger, I am a tiger. Okay, so stop baying and stop running away, act like a tiger. Okay, that's the role of a teacher. Okay, so to bring out that tiger in yourself, not like the goat who runs away, but who is ready to take the challenges. And I think that's the role of education, is to help people realize their true self and their true impact, because being focused on a job is being like a goat. And you cannot blame that student for doing that, because that's how they have grown up. But as a teacher, that's your job, and my job too is to let them know that you are a tiger, you can do better than just going after a job and preparing yourself for a job. There is a bigger world out there, and there is a bigger contribution you can make than just sitting at a desk and doing a 9 to 5 job. Okay. So yes, convergence will have its problems, it will have its challenges, but I think so for example, if you look at Silicon Valley, right, what made Silicon Valley? That particular ecosystem has not been recreated anywhere else. I guess Bangalore and Hyderabad to some extent have tried to copy it, and I guess to some extent Chennai also. They have tried to copy that model, and they are sort of on that path to realizing Silicon Valley here in India. But if you think about it, having lived in Silicon Valley and having lived in Texas, in Boston, in Mississippi, I have roamed around a lot in the US. One thing that strikes you is the mindset of the people. At the end of the day, what really made Silicon Valley possible is a group of people with a similar mindset coming together. It all starts in the mind, really. So if you think about convergence as a concept, it's also about the mindset. It's how you look at your contribution to society and how you live as a citizen in the society. That's what convergence is about. Okay. So I guess I have about 10 minutes. Okay. So let's do some. Let's go through some basics. And by the way, at the end of the day, just because I am telling it, you don't have to accept it. You can differ with me. You can have a different opinion. I think following a herd mentality is bad. That goat mentality. Carving out your own way is also one way of doing things. So if you have a different approach to life, or if you have criticisms of this, it's all the better, because it's criticisms that makes things better, that improves things. Okay. So let's just do the laws of thermodynamics, and then we will get into the modes of heat transfer after lunch. Okay. Well, before I go to this slide, what is the first law of thermodynamics? Go ahead. You all know this. You shouldn't be staring at me. I should hear 50 voices telling me right now. It's conservation of energy. Energy cannot be created or destroyed. What is second law? Come again? Not really. If you look at the second law statement, there is no word entropy. There are two statements of second law, right? Kelvin Planck and Clausius, and I always get confused. Whenever I am teaching it, I actually have to go read the book and make sure which one is the Kelvin Planck and which one is the Clausius. Okay, let's just forget Kelvin Planck, let's just forget Clausius. You are explaining it to a fourth grader. How do you explain second law? First law is easy to teach, right? Energy is always there. You are not creating it, you are not destroying it, it's always there. How do you explain second law? Go ahead. Perfect, yes, that's the second law, really. Kelvin Planck and Clausius, once I realized what second law was, I said, what garbage, why do I have to read the Kelvin Planck and Clausius statement, right? So it's as simple as that. Spontaneously heat travels from a hot body to a cold body. When is it violated? Can you violate second law? Or in other words, does heat travel spontaneously from a cold body to a hot body? Can you think of a situation when it happens? You all have taken fluid mechanics, right? Compressible flow, gas dynamics. It happens in gas dynamics. Heat actually goes from a cold body to a hot body. Though it does not violate second law though, but heat does travel from cold body to hot body spontaneously. But work is involved, and it's not very explicit. Do you know how? Does Rayleigh line and Fano line make a sense? Right? When you plot that, when you go through that nose of that plot, heat actually travels from a cold body to a hot body. So what does second law state? If heat has to travel from a cold body to a hot body, what do you need? So where does the work come from? Come again? No, the gas dynamics varies electricity. So where does the work come from when it comes to compressible flow? Come again? I mean the viscous effect is what is causing the heating, but you need some kind of work, expansion work, right. So there is actually a pressure change, and so pressure does the work. There is a PDV work that comes in actually, okay, that causes the heat to go from a colder gas molecule to a hotter gas molecule. Okay. So, so second law actually is very simply stated. It goes from a spontaneously goes from a hot body to a cold body. Now, what is the implication of this? Okay, the implication of this is not all energy is created equal. The sum total of it is constant, but some energies are of a higher quality than some energy, and so the determinant of that quality is entropy or temperature. Okay. So, if I have 100 joules of heat, the 100 joules of heat at 500 degrees Celsius is actually a better quality heat than 100 joules of heat at 100 degrees Celsius. Okay. And work is a better quality of energy than heat anytime, because you can spontaneously convert work into heat, all right, but you cannot convert heat into work. You have to cannibalize a part of the heat, make it lower quality in order for you to extract work out of the system. Okay. So, that is your Kelvin Planck statement. Okay. So, anyway, so that is second law of thermodynamics. What is third law of thermodynamics? Come again? Oh, I did not start with the zeroth law, I am very sorry. Zeroth, what is zeroth law? Come again? Thermal equilibrium. So, what is the implication of the zeroth law? So, it defines the concept of temperature as a property, okay, of substances essentially. Okay. So, coming to third law, what is third law? I am going to blame the KGPites here. You all should know better, because one of the things I really loved being a student here was we had to take probably what 3 thermodynamics classes. I do not think we do that anymore. So, what is the third law of thermodynamics? Okay, entropy is constant. In certain situations, it becomes 0. Okay. So, as you approach absolute 0 for crystalline solids, entropy becomes constant. What is the fourth law? Well, fourth law is not very formal. It says that you can never reach absolute 0. Okay, that is the fourth law. What is the fifth law of thermodynamics? That is the fifth law. All right. Okay. So, I guess we are done, right? I can wrap it up for now. Yeah, let us wrap it up. We will start with heat transfer in the second half. All right. So, okay. Thank you very